Okay, so we left off talking about creatures that live within glacial environments. So we have three photos here. Two of them on the left show us ice worms that actually thrive in glacial environments. But we also have a bacteria called watermelon algae that forms on the surface of ice. And oftentimes they form in the spring as a result of melting ice, and it smells somewhat like watermelon, but it looks like it's like a pink Kool-Aid on the actual snow itself. So it's a algae that forms as a result. Okay, so we're going to go ahead and shift gears here and start talking about continental glaciers and the vast effects of continental glaciers on the landscape and also on continental plates. Now, 6,000 years ago, before presence, we had large quantities of continental ice over North America and also Northern Europe. We can see that this map here delineates the regions of ice, but imagine we had miles and miles and miles of ice sitting on the continent, on the continental plate, so the crust. Now, the weight of that ice is going to start to bow down the plates due to just the vast size and weight. Now, over time, when the ice starts to melt away, the continental crust is going to start to rebound. And we call this an isostatic rebound as a result of the ice no longer being there. And so it's this kind of upward movement resulting in the loss of ice on the surrounding terrain. And we'll come back to that one in just a second. So the next couple slides, we're going to talk about the types of postglacial remnants that we see as a result of our continental glacier. So remember that the continental glacier covered up large areas with hundreds of miles of ice. So isostatic rebound is going to have a huge effect. But we also see features similar to the alpine glacier, but a little bit different. So we still are going to have features such as our lakes, glacial lakes that form. We call these kettles and canes, and we'll talk about why they're called this. We see that these lakes are predominant up in areas such as Minnesota and Wisconsin as a result of these ice sheets. We also see features that we refer to as eskers. So these are areas that are kind of like a river that is flowing underneath the continental ice sheet, but eventually starts to fill up with sediment. And so as a result, it leaves behind these kind of snake-like ridges of debris as a result. We also have large areas of sediment outwash. So we have plains of sediments. We have features, these debris hills in the form of, they almost look like whales' backs, are called Drumlin fields, and talk about how those are created. The first thing I wanted to point out is the Esker formation. So underneath ice, whether it be alpine or continental, we typically have areas where there's melt, so under ice river. Now over time, depending on the speed and rate of the glacial melt, it's going to start filling in with sediment. And so this cavity right here, this kind of fluvial cavity, is going to fill in, and that's going to be the Esker, that similar shapes to like snakes. So we can see some eskers in the distance here as a result. Here's another esker that we see. This is up in Minnesota, where it's a snake-like sediment ridge. So we would, just as looking at this landscape, look how flat the surrounding area is. Very different from our alpine glaciers. So, you know, the continental glacier, to scale, was ginormous, covering up almost the entire North America. And then as it started to erode and deposit features on the landscape, you know, we have all of these lakes that are formed as a result, all of these bumpy, lumpy sediment debris piles. One of those lumpy debris piles we call drumlins. And this is similar, it's an elongated, like whale shape hill that forms by glacial movement and deposition. So the axis of the drumlin is parallel to the movement of the ice. And so it's a good indication of where the ice was. We have a blunt end and we have a tapered end, and that gives you an indication that the ice was moving from left to right. And so we can also have areas where there's a basket of eggs of drumlins on the topography. So we can see the axes of the drumlin, which is a good indication of the flow of ice. We also have another drumlin that's a result of ice movement. We also have features referred to as a roche Montenay, and this is going to be where the glacial ice is plucking off debris on one end, and it's going to be moving and scraping that ice to the other end. And so we see that here. This is actually in Tuolumne Meadows, where we have some striations and glacial polish as a result. This is a feature that can be found in continental and alpine. So as a result of the movement of the glacier going from the right side of your screen to the left, we have debris that's plucked off and carried on down. The ice movement, so we have striations on the top, but we also have abrasion and polish on the right-hand side of our screen. And so here's another example of this roche Montenay. We have features in the form of kettles. Now, kettles are different than tarns. Tarn is an alpine glacial lake that's created, but a kettle is an example of dead ice that's broken off the glacier that eventually gets filled in with glacial outwash, so glacial sediment fills it in, and those kettle holes, or eventually over time, those dead ice melt and compacting those kettle holes, and the kettles will eventually fill up with water. Now, so places such as Minnesota, which is known as the land of 1,000 lakes, are all results in kettles, all a result of the continental glacier that once occupied that area. So pre-glacial landscapes, we can see large quantities of dead ice as a result. But when we're talking about glacial environments, we're talking about areas that are very cold. And so a good indication of a very cold environment, cold over a long period of time, is going to be permafrost. So this is a map that shows the distribution of permafrost across the northern Canada and into Russia and Alaska. And we can see continuous permafrost and discontinuous permafrost. Permafrost is one of those things that is very intriguing to me, since I worked quite a bit with it up in Alaska. And so basically you would be digging through a top soil and you would come across a permafrost area, and permafrost made it very hard to be able to dig holes in the soil. It makes it very hard to build and construct anything because of it could melt and cause very unstable environment. So there's areas that can have continuous permafrost up to 400 meters thick. You can have areas where that permafrost does not exist because it's underneath a small deep lake. You can have different patches of discontinuous permafrost, which is what we dealt with quite a bit up in Alaska. And so permafrost needs to exist where it's frozen for a long period of time. Now, why is it so hard to construct in permafrost environment is because eventually whatever you construct is going to be putting heat into the soil, which is going to be melting the permafrost. So if you're building a structure that's sitting on the ground itself, that structure has some sort of heat, it's going to be changing the dynamics underneath the soil, melting the permafrost. And therefore, the integrity of that structure is going to fail, as you see here with this particular cabin. Other issues to think about when construction in these alpine regions is going to be, for example, the Alaskan Pipeline. The pipeline itself has to be above the ground, and therefore these big long poles that go in the ground itself must go very deep to try to support and keep it very straight and stable in the permafrost environment. Now, the pipeline itself is 1.2 meters in diameter, and the height above the ground is from 1.5 to 3.0 meters. And the reason why it's off the ground, because you don't want to have any type of heat to melt the permafrost, but also it's checked regularly to avoid any type of catastrophic spills. There's also features that are called ice wedges that are created. And these are also in areas where it's very cold. Frozen water fills into a crack and starts to freeze and thaw, and it becomes larger, and then the surrounding area is going to disappear, and that's creating this kind of ice wedge, almost like a dinosaur tooth shape to it. Now, as we start talking about North America, we are able to identify the continental ice sheet where it once was, versus the continent and its during its glacial maximum. So during the Pleistocene, which is the last major glaciation, we had a huge continental ice sheet that sat on North America, and the largest of it, the dome of it, was over the Hudson Bay, over 3,000 meters thick. Now imagine the weight of this particular ice sheet on the North American continent. So quite a bit of isostatic rebound taking place as a result of that ice sheet shrinking quite a bit. Now during this time, this was identified as being the Little Ice Age. So again, remember that we use proxy types of evidence to help determine what past climate was like. So we have the medieval warm period, we have the Little Ice Age that helps indicate. And so during this medieval warm period, we were able to identify past settlements from explorers such as Vikings up in areas that weren't normally thought to be areas that they had traveled. And during that time, we can see abandoned settlements due to warmer periods allowing for higher latitude traveling. So northern hunting regions, we can see that there's different settlements that are abandoned at various times that are indicative of the past climate. We also, as I mentioned before, are able to use paintings to give an indication of what life was like during 1565 in the Netherlands. So to get an idea of what the climate was like. Was it cold? Was it gray? Was it long periods of ice? So to give indication of the Little Ice Age. We also use glacial evidence, ice coring, and compare them to temperature readings in tree rings and ice cores to get an indication of what types of trends were taking place over a period of time. So here we are looking in the Northern Hemisphere. This data is coming from tree rings, corals, ice cores, and historical, and comparing it to historical records. And they complement each other in looking at the overall trend that's taking place for temperature. So notice we see temperature has been rising over the last 100 years, 200 years. We also see in photos the movement of glaciers, and I'll be providing you guys with a video to watch, two videos. The first one is going to be looking at an area in Norway that is having the isostatic rebound, where Norway is still responding from the amount of weight of the glaciers, and as a result, you see movement of the clays, which is referring to as quick clays. And so there's a 20-minute video that you guys will be watching in Norway, and then there's also a 5-minute video that you'll be watching of large ice or glaciers calving off and the size of Manhattan. But recreation photography is very powerful in looking at what life was like 100 years ago to what we currently see today. We see this all the time with glaciers, a really good indication that alpine glaciers are shrinking, continental glaciers are shrinking, and that's a huge devastation because we know glaciers trap fresh water, and it's almost like this natural reservoir that allows for this continual cycle of melt and accumulation, ablation, accumulation. But if the world's glaciers are disappearing, we are going to be losing that capability to store that fresh water. And so the sad thing is many of these alpine glaciers could disappear within our lifetime. Here we are looking at the Portage Glacier in Alaska before 1914 and 2004, glaciers in Peru. So it's this global trend that's existing with alpine glaciers. So I'm going to go ahead and stop there. I have 2 additional videos that I want you to watch in combination of lectures, and I'll go ahead and post the study guide online.